The Scientific Advisory Panel is preparing a background note on methane mitigation and how the Climate and Clean Air Coalition can help to move the world onto a 1.5 degrees C consistent pathway. In this discussion, a few members of the Scientific Advisory Panel consider the different aspects of methane and its role as a key emission causing near-term climate change and as a precursor of ozone formation causing significant impacts on health, human health, and on ecosystems. Okay, we have a focus on methane because it has a number of very important impacts. It has a big impact on climate change, but also it is a precursor for ozone formation, which has important impacts on human health and also on crop yield. Drew, would you please tell us about the significance of methane in terms of its climate impact?
So methane, including the ozone formed from methane, contributes to warming because both methane and ozone are greenhouse gases. And if you count all of these direct and indirect impacts, methane is the second most important contributor to warming, with about 40% of the change in the Earth's energy budget to date. So since the planet is warmed by about 1 degree, one can say that roughly methane is responsible for about 0.4 of a degree warming thus far.
Thank you, Drew. Now, the methane is one of the substances which leads to ozone formation and has health impacts. Ravi, would you please take us through the link between methane and ozone and then how important it is for human health impacts?
Thank you, Johan. Methane, as you know, is a background ozone producer. It produces ozone across the globe. Ozone is made in the atmosphere with one of the key ingredients being substances such as methane, and it has been known to be a bad pollutant for a long time. In fact, it's one of the earliest studied air pollutants, and it affects lots of people. It's estimated it's roughly about 1 million premature deaths from respiratory diseases due to ozone pollution. Also, it disproportionately is affecting developing countries compared to the OECD countries.
Thank you, Ravi. And one of the impacts which is not so widely known or understood is the impact on vegetation. So ozone is toxic to the growth of different plants, including many crop species. So, for example, if you take soybean and wheat and rice and maize, which are all important staple crops, then globally, current levels of ozone lead to somewhere between 3 and 15% reductions in yield for these crops. So it's very significant.
Methane also is responsible for effects on crops via the climate change it induces. And so it's pound for pound tends to have a much greater impact than the equivalent climate effect of other emissions, such as, say, CO2 that would cause 1 degree warming. If you got 1 degree warming from methane, plus all of the ozone change due to that methane, you'd have a much larger detrimental impact on agriculture than you would from warming induced by another greenhouse gas.
So Lisa, it's well known that ozone affects crop yields, but there are other impacts with important consequences for climate change. Perhaps you could elaborate.
Yeah, that's right, Johan. In the same way that ozone is going to be reducing the biomass of crops and therefore also affecting the yield of those crops, ozone is also going to be reducing the biomass of all ecosystems which are exposed to elevated ozone concentrations. And some of those ecosystems obviously hold an awful lot of carbon. So if their biomass is reduced, then you're going to see increases in the CO2 concentration in the atmosphere because there's less carbon being held in those ecosystems. And this is a really important thing because it's been estimated that world's land ecosystems are currently slowing down the global warming by storing about 30% of human released CO2 emissions every year. And there was a study back in 2007 which showed that over the past century, this indirect increase in CO2, which is caused by those ozone impacts on biomass, actually contributes more to radiative forcing than would be caused by the change in ozone itself.
Thank you very much. Right, so we've talked about how important methane is in terms of climate and health and crop yields. And so it's important for us to understand the sources of the methane in the atmosphere and then to consider what we can do about it. So Drew, would you walk us through the different sources of methane and which ones ripe for control?
Yes, thank you, Johan. So the largest single source are natural emissions from wetlands, primarily in the tropics. There are other natural sources such as seepage from geological sources in the ocean and the land and termites, etc. But altogether, the anthropogenic sources are larger than the natural, which is in some way good news. That means that things that are under our potential control are the dominant players in total methane emissions. And within those, there are three very large sectors. There's agriculture, fossil fuels, and waste. There are also small emissions from biofuels and from burning. But I'm going to stick to talking about the three key sectors. Agriculture is the single largest, and that is dominated by livestock. Within the livestock sector, cattle are the largest by far component of methane emissions. All ruminants lead to methane emissions, but cattle, due to both their numbers and the volume per animal, really dominate. Rice is the other substantial source from the agricultural sector. When we go to fossil fuels, it's all three of the main sources of fossil fuels: oil, coal, and gas. From coal, it's mining activities, both abandoned mines and those that are still in use. From oil and gas, it is for oil, it is the extraction process when gas is found simultaneously and vented or flared away. For gas, it is both the extraction and the downstream use, the storage, transmission, and eventual distribution throughout, in many cases, very old infrastructure. For the waste sector, the solid waste is the dominant source with a lesser contribution from wastewater. And those are really the key sectors for methane emissions that are under human control.
Thank you, Drew. Maybe we could consider the changes in the concentrations of methane in the atmosphere and how that relates to those different sources. Are the biogenic, are the natural sources increasing, or are they pretty stable? And is it the anthropogenic sources which are increasing and causing this increase in methane concentration in the atmosphere? Could you give us some background, please?
I can give you some background, yes, thanks, but not a clear answer to that excellent question. And there's a lot of debate in the literature. Clearly, the observations show that methane amounts are going up after a period when they were fairly stable. We know that there's been a massive increase in the use of natural gas in many countries in the world. We also know that it's extremely difficult to know what's coming out of that sector, and often the bottom-up reporting is inconsistent with top-down measurements when, say, aircraft fly over, or estimates are made from satellites. We also have isotopic information, which is not conclusive, but suggestive that much of the recent rise is due to biogenic sources, which could be either natural wetlands responding to a warming climate, so they would be indirectly human-driven, or they could be increased food production leading to more biogenic methane from agriculture, which would primarily be increase in emissions from cattle. So it's really an interesting and hotly debated topic, what's causing this rise, but in either case, we are, although we're not clear on the contribution of individual sectors to the recent growth, we are clear on the relative amounts of emission from the three major sectors.
And so would you say that it's likely that the largest driver of emission increases is the anthropogenic part?
I do think it is the anthropogenic part, yes, but it is difficult to parcel it out between biogenic and fossil sources.
So why don't we turn to the potential reductions that we can make to the different sources of anthropogenic emission, and where we see the potentials to reduce this methane and try and pull this trend down, and thereby help to contribute to achieving the 1.5 degrees C goal. Drew, could you take us through where the potentials lie in terms of the reductions in methane that's possible?
Yes, I'd like to talk about the potential on a sector level and within the fossil sector. So again, oil, gas, and coal. There is enormous potential with technical measures to bring down the vast majority of methane emissions. Not only that, but there's really good news here is that the vast majority of those technical measures come at either low cost or in many cases, more than half of them come at negative net costs. So we could really get a enormous reduction in this, the second largest source of methane emissions from existing technology at low cost. And then further positive news, the waste sector is a very similar status, especially for solid waste. Wastewater can be a little more challenging, but within the larger solid waste sector, we can control the vast majority of emissions with existing low cost, or in most cases, negative cost control measures. So we really have the potential to pull down to extremely low levels consistent with the 1.5 degree scenarios, the fossil fuel sector and waste sector scenario emissions with existing technological measures. Within the largest sector, agriculture, there are control measures that are estimated to be able to reduce about half of the emissions from rice cultivation, and about a quarter of the total come at negative cost. So that's somewhere in the middle. Within the livestock sector, there are fewer technical options. There are measures to improve herd health. There are feed changes, but all of these on a global scale are estimated to have fairly modest potential to reduce emissions from this sector. So within the agricultural sector, to achieve something like a 1.5 degree methane scenario, it really requires going beyond purely technological measures and into behavioral changes, in particular to reduce demand for carbon-intensive cattle-based foods.
So Drew, there is a regional component to this, isn't there, in terms of the potential mitigation, even in sort of animal husbandry? Perhaps you could touch on how this varies according to where you are.
Yes, thank you, and that's a great point. And there are a few sectors, including agriculture, but also including the coal mining, coal mine-related methane emissions that are highly regionally inhomogeneous. And the cost and the amount of mitigation that can be achieved varies enormously depending on where you are, for coal mining, for rice cultivation, and for livestock. And so in particular, some areas with low intensity raising of livestock have the potential to adopt the more high intensity management practices and greatly reduce yields. It's those countries where the higher intensity practices are already in place that don't have enormous potential and bring the global average down to such small numbers like we see when we look at these total potentials. So in some regions, there are also big differences in how livestock contributes to social well-being, whether it's part of a large business concern or whether it's much more how people store assets, and regions where dietary shift can promote good health and well-being, such as North America and Europe, where consumption tends to be far higher than that recommended by the WHO, and other places where protein deficiencies exist and dietary shifts are not warranted. So both the potential from behavioral and technical measures vary enormously by region.
And I suppose you could say that there are many different scenarios for how these different measures can play out. And so what's shown here, how does that compare to other estimates for the degree of reduction in that agricultural sector?
These technical mitigation potentials evaluated by EASA are at the low end of the potential in other studies, largely because the other studies go beyond the limited amount you can achieve with technical potentials and include more behavioral estimates. But estimates published by other groups are similar, say the US EPA, when they only look at technical potential, but when they expand beyond to include behavioral changes, especially dietary preferences, they can achieve far larger potentials, double or triple, quadruple of what's shown here. And that's really required to follow a 1.5 degree pathway.
Well, let's have a look at the IPCC 1.5 degree C pathway. And we have here the famous figure which shows the need to reduce emissions of methane, but also other substances, especially carbon dioxide and black carbon. Could you tell us, how does the mitigation that we're discussing for methane relate to the scenarios here for CO2 reductions and methane emission reductions required to achieve that goal?
Well, to achieve the 1.5 degree goal, we really need to get CO2 down to about net zero by the middle of the century. And the only way to do that is to get rid of coal extremely rapidly, largely within the decade, and then to also shift over the coming couple decades away from oil for transportation and gas for power. So as we do that, that will naturally contribute to some of the methane emission reductions. Things like downstream gas release don't occur in as much volume when there's not as much use of gas downstream. But other things like release from coal mines will still be emitting methane even when they're abandoned, and so require specific measures. So what's shown here is that the methane declines consistently in time with the CO2, but it doesn't reach net zero levels, in large part because agriculture is not as amenable to getting down to low levels while still feeding a growing population. It's the same reason nitrous oxide levels shown there in the lower right don't go down very much at all. But the fossil methane decreases as a combination of both fuel switching, energy efficiency measures that are part of the CO2 mitigation policies, and policies focused very specifically on methane, such as dealing with abandoned coal mines.
Thank you for that. So if we look at the mitigation that you had shown, the potential that had been developed by IASA, we've got reductions in fossil fuel emissions consistent with these large reductions that you said, but it seems that the level of reduction implied by the 1.5 degree C pathway cannot really be achieved without more than technical measures in the agricultural sector. So it would seem that those behavioral measures would be necessary if we're going to get it down to those levels in the next decades, in 2030 and beyond, which are implied by that IPCC report. Is that right?
That is correct. And even in the case where you had maximum application of all of the technical potential, and you can see that you're just barely within a 1.5 degree consistent pathway, this would only work for the one decade, the coming decade. And then if you've used up all of your technical potential, you would have to go well beyond that to things like fuel switching and behavioral change in order to stay on that 1.5 degree pathway beyond 2030. So it's extremely unlikely you could get there with only technical measures in the first decade, but even if you did, then you would definitely have to go beyond in the following decade.
So it would seem that if we are going to reduce methane in a 1.5 degree C consistent pathway, then we need to pull out all the stops for the fossil fuel and waste, but that we've got this rather tricky emission in the agricultural sector, which we need to spend a bit of time, understanding how we're going to address those emissions successfully as well.
I would agree with that. And I would say that, the good news for fossil fuel and waste is the analysis showing that not only is the technical potential available, and if we pull out all the stops, we can get there, but that the majority of these technological approaches are very low, or in most cases, even negative costs. With agriculture, it's not so much the economic cost for mitigation, but you're right, we really need to think hard about changing lifestyles in order to bring down agricultural sector emissions, or we cannot really hope to get to a 1.5 degree pathway for methane, but really that's part of the entire package of greenhouse gases. So we can't really hope to get there for the world as a whole without these kind of behavioral changes, which include how we use the land.
Thank you very much, Drew. So if we just consider the pathways that we need to take in order to get us on the right path towards 1.5 degrees C, Drew, could you give us an idea of how we're doing in terms of the methane emissions, but also the related CO2 emission reductions that are implied by the 1.5 report? How close are we to following those trajectories?
Well, that's a good question, and it depends on a little bit on which trajectories you look at. And so by definition, the 1.5 degree pathways only start to implement policies after 2020. This makes them hard to compare with, but they envision enormous decreases in the coming decade. And our trajectory is unfortunately still upwards. So if we compare back with the scenarios from the previous generation, when we were looking at scenarios where we implemented policy starting in 2010, and by now to be on a low warming pathway, say 2 degrees, we should have dramatically brought down methane and CO2. And instead, both of these are going up, and methane is going up, as we've seen, faster now than it was a decade ago. So not only are we not mitigating, we're in fact moving in the opposite direction for both these gases.
So to me, that implies that the CCAC's got a lot of work to do then, especially if we're going to achieve any of this by 2030.
Yeah, CCAC and UNFCCC, right? But both have their work cut out for them.
Well, thank you very much.